mentioned.
Okay.
As it was mentioned that I think some video will be the video is there and you will be presenting through that video that we have already uploaded in your link. And for the question answer session, myself Devaprasad De, I will defend the question answer session.
Excellent.
So I'm staying with you. I'm staying with you. Okay. Till the question answer session is over for this first paper, Hyper. Thank you, sir.
Presenting a part of our work on an efficient design for a hardware accelerator for hidden periodicity detection using Ramanujan sums. The following slide contains the outline for our presentation today. Periodicity detection of any discrete time signal x of n deals with finding a p for which x of n will be equal to x of n plus p, given p is the smallest of such numbers. Now, two or more different periodic signals can combine themselves to form another signal with a different periodicity. In such cases, the periodicity of the basic signals are termed as the hidden periods. The period estimation problem, which can be defined as estimating the periodicity, including the hidden periods, for any noisy signal having a time-varying periodic nature, is shown to have an elegant solution using Ramanujan filter banks. We use the same to construct our hidden periodicity detector. Here we show a basic hidden periodicity detector in action. Ramanujan filter bank RFB based on Ramanujan sums was introduced as a tool for identifying periodic patterns in data. RFB based periodicity detection was shown to have computational advantages over other methods and also reveal localized hidden periodicities in real-time data and process signals with time-varying periodic nature. It was also shown to be of interest in real-world applications like detecting seizures using EEG data or to identify repetitive structures in protein molecules, etc. Our motivation was to design and implement a fast, cheap, and energy-efficient hardware accelerator for hidden periodicity detection based on RFB. Now, we take a very brief look at what is Ramanujan filter bank. Ramanujan sum is a trigonometric summation defined by Srinivas Ramanujan, defined as the summation of e power j 2 pi kn by q for k equals to 1 to q, where k and q are co-prime integers. RFB was a compact approximated representation of the use of Ramanujan nested periodic dictionaries to solve the periodicity detection problem, represented by a group of filters from 1 to Pmax, Pmax being the maximum period which can be detected, with each filter having the impulse response of HPN. Here, L is the number of periods of CPN. The following structure shows the construction of the periodicity detector, which was proposed using the Ramanujan filter bank by Vaidyanathan et al. The output for each channel corresponds to the strength of the corresponding period in the input. We first propose a basic microarchitecture for the HPD based on RFB, which we improve upon with incremental modifications to obtain the rest. Our idea behind having incremental improvements was to have a quantitative understanding of the impact of every change. The first microarchitecture, architecture A, uses 4 stages. Block 1, the RFB, which is realized using a direct form structure, and the Pmax Ramanujan filter will thus use LPmax number of multipliers and LPmax minus 1 number of adders. L is referred to as the localization parameter. Smaller L means better time localization but a poor period resolution, and vice versa in the output period versus time plot. Block 2, divider. Here we use a non-restoring algorithm for the fixed point division as it has inbuilt support for signed arithmetic. The divisor is a fixed value for a given channel f of p, which is the penalty function helps to extract the smaller periods with greater strength. Block 3, squarer, which is made using a combinational multiplier. Block 4, moving sum filter, which is also realized in a direct form structure with a smoothing parameter s, which controls the time spreading of strength corresponding to period p in the period versus time plot. The output yin of channel I gives the measure of the strength of period I in the input x of n, and the strengths of the periods are plotted with time to get the period versus time plot. In architecture B, we modify the filter structure of block 1 and block 4 to reduce the critical path delay of the structure. We use the transposed realization structure because their self-pipelined operation of a broadcast structure reduces the critical path delay. The microarchitecture for the rest two blocks in architecture B remains the same as in architecture A. We also pipeline the overall microarchitecture to further improve operating frequency. In architecture C, we try to reduce resource utilization. Thus, we implement the block 1, the Ramanujan filter bank as follows. We use the periodic impulse response of the pth Ramanujan filter to realize the filter using only P multipliers instead of LP. We switch to a feedback structure reducing adders from LP-1 to P+1 in expense of P+1 resistors. A pipeline stage is added in between to maintain the same critical path delay in block 1 as in the earlier case. The structure plot block 2, 3 and 4 remain the same as in architecture A. In architecture D, we use the multiplierless RFB proposed by Tenethi and Vaidyanathan for the Ramanujan filter bank in block 1. The multiplierless RFB itself has 4 sections. Pre-filter and post-filter sections are realized using their direct form structures. The T matrix combines the inputs in different ways to obtain the outputs and is made using combinational blocks. For section 2, we use a simple combinational multiplier. This structure for the RFB further benefits our aim to reduce resource usage. Implementing architecture D reveals the bottleneck for pipelining as block 2. We thereby implement a simpler and faster divider using a multiplication operation. The divisor f of p being a constant for a particular channel can be reciprocated and multiplied to the output of block 1. Adding the faster divider causes the critical path to shift to block 1, so we pipeline the multiplierless RFB to improve frequency of execution. We also use a feedback structure for the moving sum filter to reduce resource usage.
Hi, I am Chandrachud and I will be presenting the remaining portion. In this slide, we present the experimental methodology we followed in implementing the microarchitectures for the accelerator. We start by having a software implementation for the designs in MATLAB, where we test them on different signals for different applications. We then moved on to implementing the RTL for the microarchitectures using Verilog and simulated its functionality and timing constraints using ModelSim. Now, for an n-sample input, we would like to have an n-sample output for the period versus time plot. Thus, we take additional samples to compensate for the group delay due to the two filter structures. So, the total input samples to be taken is as follows. Finally, we map the RTL for the microarchitectures to the open NAND gate based 45 nanometer process technology, where we obtain the area, timing and power results for them using Synopsys Design and Power Compiler. In this slide, we summarize our microarchitectures and the key modifications before moving on to the results. We saw that ARC-A was a naive direct form implementation for all blocks in HPD. We tried to improve upon the critical delay of the structure in ARC-B by using transposed realization structures and pipelining the system. In ARC-C, we used a resource-efficient implementation for the RFP, which would lead to area and power savings. We furthered this idea by using a multiplierless RFB structure in ARC-D. In ARC-E, we made our divider simpler and faster and pipelined our RFP structure to improve upon the critical delay. We now plot and compare the various design parameters like power, area, etc. for the microarchitectures when mapped to the 45 nanometer process technology for this given set of parameters. We see that there is a steady improvement in each design parameter from ARC-A to ARC-E, except latency, which shows degradation from ARC-A to B to C due to pipelining, because of highly unbalanced timing requirements of the independent stages. The critical stage being the faster divider, we don't see any improvement in latency when different structures of RFB are used in ARC-C and ARC-D. But implementing a faster divider in ARC-E significantly improves our latency. The improvements in other parameters are expected as per our modification, though the different microarchitectures here we have summarized above. The power in ARC-B degrades due to increased internal cell power for the transpose filter structures, which improves when we use a resource-efficient structure for the RFB in ARC-C and T. We plot the area delay power product ADPP for the architectures as a qualitative measure of the quality factor for the design. We see that the ADPP for ARC-E is the smallest. Thus, ARC-E is overall our best microarchitecture. In this slide, we present the results obtained when we applied our accelerator to some of the applications of hidden periodicity detection. We start with the detection of absent seizures using an EEG output signal. Absent seizures are characterized by a 3 Hz periodic spike, which is diagnosed by detecting such periodic patterns in a patient's EEG. We generate a signal EEG-S of 20 seconds with an absent seizure event from 10 to 13 seconds and sample it at a rate of 100 samples per second, causing the 3 Hz spikes to appear as periodic pattern with period of around 33 samples. We also generate another signal with multiple absent seizure EEG-M to test the sensitivity of the accelerator. Notice the high strength of the output in the period versus time plot around period 33 for certain time durations, indicating the absent seizures at those intervals. Next, we look at the detection of tandem repeats in protein. Here, we apply our accelerator to detect tandem pentapeptide repeats in protein 2BM4 to reveal its important structural and binding properties. We map the amino acids to real numbers using Kite-Doolittle hydropathy scale. We also apply it to protein 3D-U1 et al., where we also look for pentapeptide repeats using the period versus location plot and the insertion loops using the output power versus time plot to extract information regarding its structure. Notice the high strength of the output in the period versus time plot around period 5 for both of these because of the pentapeptide repeats. We move on to tandem repeats detection in DNA. Here we map the nucleic acids A, T, G, and C to every permutation of number 1, 2, 3, and 4. We apply our accelerator to the human frataxin gene intron 1 U43748 to detect Friedreich's ataxia using period 3 repeat. The triplet repeat GAA present in the first intron of this gene is responsible for the neurological disorder known as Friedreich's ataxia. We also apply it to AC010136, where we can identify markers of period 4 repeats for DNA fingerprinting and other forensic applications. In this slide, we compare our accelerator to the software implementation for ARC-E. We define a quality metric ALQ, application level quality, to quantify the accuracy of our accelerator to its software implementation. ALQ is being defined as follows, where NCD, NFD, and NYREF refers to the correct detections, false detections, and number of detections in reference matrix of the software. The following table presents the ALQ for the applications we have presented before. We adjust the definition for ALQ for EEG application as only the period 33 repeats are relevant. Also, we use the two best permutation for the DNA application for both software and hardware cases. Notice that the ALQ value has a almost at worst case of 5% degradation. Now we present the speedup provided by the hardware accelerator based on ARC-E. The following table presents the time of execution for both software and hardware implementation for the applications we have mentioned before. We plot the speedup from the accelerator and see it provides a minimum speedup of 4.6 into 10 to the power 3 for one of the DNA applications, and a geo mean value of 6 into 10 to the power 4. Thus, our accelerator with only a maximum of 5% degradation in quality provides such high value of speedup. To summarize, we implemented 5 different microarchitectures for the accelerator and compared them on area, timing, and power aspects, showing how we improved upon these parameters. The performance of the proposed hardware accelerator is then presented with the help of 3 important practical applications: detection of absent seizures, detection of tandem repeats in DNA, and protein. We also saw that minimum and maximum speedup achieved are 4.6 into 10 to the power 3 and 4.4 into 10 to the power 5, with a geo mean value of 6 into 10 to the power 4 with only a worst case deviation of 5% in quality. This concludes our presentation.
Thank you very much. So I think Devaprasad is online. So any questions?
Yes, sir. Yes,
Yeah.
sir. Good morning, sir.
So from the audience side, we don't have any questions. Maybe Session Chair may ask 1 or 2 questions on the way of
Yeah.
audience.
Sure. Regarding your the different architectures that you have evaluated, right? So the one which you had shown as with respect to all the metrics, this is from silicon or is it from the emulator?
Pardon, sir?
The results that you had shown,
Yes, sir.
software versus the architecture E, right?
Yes, yes.
This is a silicon implementation or is it pre-silicon?
Sir, actually, we have implemented it in, I mean to say, in FPGA, and that is
Okay.
basically silicon-based.
Yeah. Okay. So it's an FPGA. Okay. And do you also have a comparison of power when you are comparing software versus?
Yes, 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 sir. We have checked it, and we have done it in Synopsys Design Compiler and Synopsys Power Compiler, respectively.
What I mean is between your software implementation and your hardware implementation.
It is more or less a deviation of 5%.
5%. Okay. 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 And maybe you had mentioned this. What's your false positives?
False alarm.
In your hardware architecture.
It is close to, I think, means so far I can remember, 3%.
Okay. And what's the let's say the level at which it can handle? What's the complexity till which it can handle? Or how do you define that? What's the limiting aspect of this architectures?
Sir, actually, what we have done, we have just checked the means available literature that is given in references 1, 2, and 3, and we have tallied our architectures. Means we have verified our architectures with the software results that that are given in paper 1, 2, and 3 in the reference that we have already mentioned, and we have got the results quite. Good results we have got, and we have checked that architecture E is outperforming the rest of the architectures, and we have actually evolved architecture E starting from architecture A through E.
Okay, thanks. Good work. Thank you.
Thank you, sir. Anything else, sir, would you like to ask?
From my side, it's okay. Aryabhatta,
Okay.
do you think there are other questions from anybody else?
No, I don't have any questions. Okay. So we can proceed for the next.
Let's conclude this paper. Thank you very much, Devaprasad.
Okay.
Thank you very much.
Okay, welcome, sir. Have a nice day. May I leave the session?
Yeah, if you want it.
Okay, thank you, sir.
So we'll switch to the next paper. It's a 5 nanometer wide voltage range, ultra high density SRAM design for L2, L3 cache applications. So this will be presented by Manish Trivedi from MediaTek, Bangalore.
No, Krishnanand also there, I think so.
Yeah.
To VLSID 2021. I am Sriharsha from SRAM Design Team MediaTek Bangalore, and I am going to talk on the 5 nanometer wide voltage range ultra high density SRAM design for the L2 and L3 cache applications. First, I will introduce the cache, SRAM and the high density bit set. Then I will go through the challenges in the L2 design, mainly write assist and the self time. I will go through the problem statement and solution for each one of them and discuss on the results and the conclusion. So here we have a CPU core. Whenever it needs to access any data from the main memory, instead of accessing it directly from the main memory, which is time consuming, it stores the data in the different cache levels and accesses it. So here L1 is generally the fastest and L3 is the slowest cache. Generally SRAM is used as the cache because it is the densest storage element in that particular technology. In the SRAM, we have the bit cell array and the periphery logic. So this is the sample 60 bit cell. So in bit we have two variants. One is the high current and other is the high density. For our L2 cache application, because the size is high and also the frequency is less than L1, we are employing the high density bit cell. So here I have a HD bit cell. To write into this bit cell, I need to discharge my bit line from 1 to 0 so that the bit flips from 1 to 0. So on this graph I have the write margin at the SFG corner. So what write margin tells is it quantifies the writability of the bit cell. What it means is whenever bit line is discharging from 1 to 0, the voltage at which the bit cell flips is actually the write margin. So here on the x-axis I have the voltage from 0.45 to 1 volt, and y-axis I have the mean by sigma. So what this graph is telling is basically whenever my voltage is above 0.7 volt, we can see my mean by sigma is 7. That means I am able to guarantee the 7 sigma yield. So similarly, when the voltage is below 0.7, the mean by sigma is less than 7. That means I will not be able to guarantee the 7 sigma yield, and we will be requiring the assist for the yield improvement. So there are different write assist technique: word line boost, VDD collapse, VSS boost, and the negative bit line. So all four of them either increase the pass gate strength and the pull, or reduce the strength of the pull up. Here we are employing the negative bit line based write assist because it is both area and power efficient. So NBL write assist has its challenges. One is the area cost due to the boost capacitor size, other is the overboost and the underboost concern. So we'll walk through in the next slide. So this is the simplified boost NBL boost circuit. Here we have the boost capacitor. Whenever we trigger the boost capacitor, it pumps the charge it stored onto the bit line, thereby producing a negative voltage on the bit line. So here on this graph, I have on the x-axis I have the our L2 cache need to work across the wide voltage range of 0.45 to 1.05 volt. So in the previous slide we have seen that our HD bit cell won't be able to function if the supply is below 0.75 volt. So that's why we have fixed the SRAM supply at 0.75 and varied the supply of the VPERI to ensure that our SRAM works from across this wide voltage range. So our VPERI range is from 0.45 to 1.1 and our SRAM range is from 0.75 to 1.1 volt. So on this graph here, on the x-axis I have the voltage and y-axis I have the negative boost. So here if I tune my boost capacitor to pump a 100 millivolt boost at low voltage, if the same boost capacitor will pump a very high boost, that is approximately 250 millivolt boost at the high voltage. So this is the overboost scenario because actually it causes the reliability issue because of the voltage across the column mux will be greater than what the technology specified, and also this overboost will also trigger the unselected row getting selected. So similarly, if I tune my boost capacitor at high voltage, it will cause an underboost at the low voltage. So that is the issue with the existing NBL solution, that the overboost and the underboost concern. So the solution for this is basically if we shift our NBL logic from VPERI domain to VSRAM, because of the limiter range only from 0.75 to 1.1 volt. Here if we tune our boost capacitor at 0.75, there won't be any underboost scenario, and also because we need a much smaller boost cap, if we tune our boost cap at 0.75 volt, at high voltage it won't lead to any overboost scenario. So by employing this method of shifting boost logic to VSRAM, we are able to have the optimal boost across the PBT. So also we are able to get the area benefit, because the boost cap required at 0.75 volt to generate 100 millivolt boost is much lesser compared to the boost cap required to produce the same boost at the 0.45 volt. So here this is the same circuit here as the previous, but here we have the right mask also included. So here in the this is the circuit of the NBL boost, which is actually employed along with the right mask feature. Here, as we discussed in previous, if we move our supply from VPERI to SRAM, it would solve the issue, but there is an issue in this circuit, so that I will try to explain. So generally we have a right mask feature. So what that feature tells is, if we have 72 bits, we want to write only for 36 bits, we can turn the right mask only for 36 bits and turn it off for the other 36, so that we can write only on the 36 bits what we require. So how the right mask feature works is, whenever right mask is 1, our DLAT and DLB, whenever right mask is off, our DLAT and DLB is 1, effectively cutting off the right circuit for that particular bit cell. So during the right mask is off, we want our boost, we don't want the boost to generate, because the reason, when right mask is off, if we generate the boost, basically because the bit line is now decoupled from this V pump node, it will inject a higher voltage on this V pump node, causing both all this N1, N2, N3, N4 transistor to turn on, and causing an accidental write into the bit cell even when the right mask is off. Okay, so that is the reason why we need to have a gating for the boost capacitor with respect to right mask. So here we have the DLAT and DLAT B at the VPERI. So if we shift both of them into the VSRAM domain and all the other logic into the VSRAM, we will arrive at our VSRAM domain solution. But the problem is, we need to use two level shifter here. So similarly, if we use if we convert W mask C at and introduce a level shifter here, that is a area overhead, because we need to introduce the level shifter for all our IOs. So for that, what we have proposed is, we shifted the logic to VSRAM and employed a clamp which triggers whenever the right mask is off. So whenever right mask is off, the boost capacitor pumps the negative voltage, but that voltage is pulled down to 0 with the help of this clamp. So by doing this, we are able to achieve address the area underboost and overboost concern, and also without any area overhead, we are able to employ the right mask feature as well. So in the next few slides, we'll talk about the self time employed in this L2 cache. So what self time is? Self time tells the SRAM when to stop to read and write. So here basically, whenever we turn the word line on, we discharge, the bit cell starts discharging, and we want our sensor to trigger at this point. So if the self time is slow, actually it causes the access time impact, and if the self time is fast, it may cause the read failure. Similarly, in case of write, if the self time is slow, it causes the cycle time impact. So our self time also need to be optimized across all the voltage range to meet the different frequency at different voltage points. So the bit cell provides us the DDC cell, which is a dummy discharge cell. So this dummy discharge cell actually helps to mimic the bit cell and its process variation. So these are the sample DDC cell. Whenever we turn the DWL on, it discharges the DBL. So here multiple DDCs are connected through the DWL, and it will discharge the DBL. So this is the existing self-time tracking. So here we have the bit cells IO and the control logic. Here we have the DDC cell. Here whenever the clock comes, it generates the internal clock, and it also generates the DWL. DWL is a dummy word line, and we need to so one main point is DWL at the VSRAM domain here. Once the DWL turns on, it discharges the DBL, and which in turn triggers the sensamp and provides us the output. So this is the existing self-time with the DWL at the VSRAM domain. So problem with the conventional self-time is, because the DWL our self-time is on the VSRAM, when we are at a nominal corner, it is 100% of the self-time is required. But when we move to the extreme dual del, because the self-time is on the VSRAM, it will cause basically read-write failure. So to fix this problem, if we have added the fixed gate delay at the 0.5 0.9 corner, but this has resulted in the increase in the self-time delay at 0.675 and 0.675 corner. So this resulted in the degradation of the performance. So to resolve this issue, if we move our self-time to vPeri domain, what will happen is that because the vPeri is 0.5 volt, it will lead to the degradation of the performance at the low voltage corners, that is 0.675 and 0.5 volt. So to solve this issue, what we have done, we have placed the self-time on both vPeri and VSRAM, thereby optimizing across the voltage range. So with this, we are able to get the 10% performance gain across the voltage range. So this is the proposed new self-time tracking. Here we have introduced the DWL at vPeri domain along with the VSRAM domain. Along with that, we have used the delayed tune logic, where we can actually tune the number of DDC cells on the VSRAM domain, both on the pre and the post silicon. So with the proposed circuit, we are able to achieve 10% performance gain with minimal area and power cost. So these are the results. So here we have the proposed technique are used in the 5 nanometer SRAM test chip, and we are able to get the 100% yield. So the benefits of the proposed scheme is we are able to eliminate the underboost and overboost scenario, and also we are able to get the 10% performance benefit because of the innovative self-time tuning. The proposed HD SRAM is validated with a 100% yield in the test chip. Yeah, thanks everyone for giving me this opportunity.
Good morning, everyone.
Yeah, thank you very much. So it's open to questions. Haribhatta, do we have some questions?
So now also we didn't got any questions from the audience, but let me ask one question from my side. So what is the comparison, performance and density comparison as compared to any NVRAM based case? So nowadays NVRAM is more popular in actually case. Many people from they are getting actually NVRAM are getting into the case. So how you compare with NVRAM in terms of density and performance?
What is this NVRAM? It is negative bit line or?
No. So non-volatile RAM. So PC RAM
okay.
RAM. So they're getting into this.
Okay. Actually, we didn't. I don't have any with NVRAM comparison. I don't have, but we have comparison with the previous technology actually.
Okay, that's fine.
So around 15% is the area benefit which we got from when we compare it with the similar design with the previous technology. That is 7 nanometer.
Okay. So okay, that's from it. Arthur can ask any questions.
Yeah. So
or from the other speaker also can ask questions if they want.
Exactly. I think please don't hesitate to ask questions. Okay. Sri Harsha, right? So the question is, what is the implication on the read margins when you implemented all that, let's say, the additional techniques for your write? What are your implications on the read margins?
Uh, yeah. Uh, so whatever the technique we have used here, uh, in the previous method also the same assist was applied, right assist was applied. Here only the domain of the assist, right assist logic is shifted from
Yeah.
periphery to the SRAM domain so that we can tune the boost capacitor uh, in a much better way. Taking that into consideration, the effect of the read effect on read as a read margin still is same in the previous technique also. Only the boost has been shifted to a different domain for better tuning.
Okay. And your new self-time method and even comment on your the shifting of your, let's say, the right boost. What are the power implications?
Okay.
Is there something, or is it something same order of magnitude?
Okay, so coming to power implication, I think basically the power because our boost cap is much smaller now, and the magnitude of the boost across the voltage range is also much smaller. Thereby, actually, the power also is lesser from the boost cap point of view. Whatever the charge implied onto the bit cell is much lower now, so that's why the power taken is also much lower in this new technique.
Okay, thank you very much. I
Yeah.
think that's if there are no more questions. So let's close this paper. Thank you very much for this good work.
Yeah, thanks, Martha. Yeah.
Yeah. So Haribatta, you can move to the next paper.
Yeah, we can move to the next paper.
Yeah, so next paper is from Synopsys. It's presented by Krishnan and Mishra. The title of this paper will be Creating Fast Self-Timing Reference Path for High-Speed Memory Designs.
Good morning, everyone. So in this part of the session, I'm going to speak about our paper on creating fast self-timing reference path for high-speed memory designs. So let me start with a bit of motivation, what actually prompted us to work on this idea. So as we know, the advent of 5G mobile technology has proven this over the time that we really continue to push for high-speed mobile systems. And typically these systems actually are not running at high speed all the time. They actually go in a high speed burst followed by idle time to conserve power for battery powered applications. So, and which is very well served by DVFS technology that we have, based on which we can alter the frequency of operation with the change in voltage. But important thing to note is that as we are able to scale the speed for these mobile processors, it is very important that we are able to do the same scaling for the interface designs like SRAMs, which is important that they actually scale good in line with these processor speeds so that we could achieve the desired throughput that we are looking for. Okay. So in this paper, we would like to show what actually limits memory speed as we increase the voltage of operation, and try to come up with a solution without actually compromising on these design robust solutions that memory designs use. Okay, let me quickly go through the basic read memory operation just to show where exactly it is limited. So they're starting with clock, and then we have intent clock generated based on which the entire read and write memory operation would work. We enable word line, and then we enable this stop clock signal. It is actually indicating the duration of read write pulse that a particular instance size would require. So which means this stop clock generation would actually is dependent on the instance size overall. So once it is generated, then it actually resets the internal clock, ensuring that that would be sufficient for the operation for that particular instance. Okay, then we enable sense amplifier, and then followed by output send to Q. Okay, so if you look at it in a nutshell, that the clock to Q path is mainly divided into these three subsections. So clock to word line and the sense amplifier enabled to Q output. Those are mostly combinational logic, which would scale well with increase in voltage. Okay, but there's this third component, that word line to sense amplifier enable, which consists of the self-time replica logic, which is important for the proper read and write pulse to be created. Okay, and that's where the most of the RC element is involved. So that might not scale as good as the logic scales. So that's where the real problem is. That should we actually remain with the design robustness that those RC elements are bringing in, or we could find a balance. So that's just what we are actually trying to see. So let me just put it a little more details. So op clock is actually that internal clock which I was talking about. So if you look at this diagram, so once this clock is generated, we have some logic delay, and then there's the driver, which is similar to the word line driver we would have, and then you would see this horizontal section. So where we have these gate loads added, which mimics the behavior and the load which actual word line would be seeing. Okay, and then followed by a pull down circuitry, which is very similar to how the bit cell would actually behave, and it would discharge the bit line, which is this section is depicting that bit line RC, and diffusion loads are actually they actually mimic the behavior that actual bit line would be seeing in bit cell. Okay, so if you look at this overall picture, there are actually two parts of it. One is still logic, and there's this good RC component involved, which actually defines this self-timing path. Okay, so if you look at this, the overall self-time time, so it is the logic component, and let me use this logic component, or also the RC component of it. Okay, so this would scale good if we increase the voltage of operation, but this might not, and that's where the limitation in speed might come in. Okay, so if we look at it in a different way, so let's see, as voltage is increasing, we know the device performance would actually get better. Okay, and T logic would scale, but the RC component might not. So the similar picture is shown by this diagram. So if you see, I'm using two different instances. One is small, where the overall path is dominated by logic. So that's why if you see that if we increase the voltage, then the access time is scaling good. So it is actually reducing with the increase in voltage. But same thing is actually not happening for a tall, thin kind of instance, which is actually dominated by bitline RC. Okay, so that's why if you see, it is not scaling as good as the small instance was. Okay, so that's where the limitation is. You are increasing the voltage, but you are not seeing that kind of a speed boost for this tall, thin kind of memory. Okay, so what could be the solution? The imperative solution, it seems that, let's say, get rid of that RC component and replace it with a logic. Then once the entire thing is logic, then it would scale well with as you increase the voltage. So let's look at it hypothetically. Okay, so in this chart I'm showing there are two different modes. One is actually a very default mode, which actually uses your logic and RC track, the classical RC tracking method that we use in our memories. Okay, and it is using some certain number of stages. Okay, so if you look at this small instance, it is actually using some number of stages. And then I also define a fast mode, which is out and out fast mode using only logic stages. Okay, so what would happen for a small instance? They would remain more or less same because it was mostly logic. But as we increase the size of the memory in vertical direction, so there's actually the taller one would actually see some RC coming in. So in this case, what I'm trying to see, let's say if I replace that RC component with some logic stages, so what would happen? So let's say in this case it was around 12, and that increased to 2025 because I'm going to compensate the RC part of it using logic, and similarly it would keep on increasing as I increase the height of the memory. Okay, but using this method is definitely not viable, because the first very obvious is you cannot actually put in so many stages, because that would actually result in increase in area, and that is also not viable, because even if you are actually working at really high speed, the variation has not really actually gone away. And there are other complications also associated with it, one of which I would talk about in one of the subsequent slides. Okay, so what do we do actually? So there are some, let's try to put together some perspective. So at high voltage, what is happening? The process variations, as I said, is reduced, but it's not completely eradicated. Okay, so if you bring in so many stages, then they bring some kind of the increased kind of variation in overall path. And it's also true that even if we have increased the voltage, then but the word line and bit line RC have not scaled as good as you would expect them to, and with bit cell read and write time, so they have gone better with voltage. Okay, so you actually try to compensate for this RC using stages is again not a viable option, as I said. Okay, and we know the bit cell performance has got better. So we understand as we increase the voltage of operation, some things are actually improving that we need to account for if we really want to hit higher speeds. But there are other components which are not scaling well, which are actually contributing to the overall robustness of this design. Okay, so we clearly see a need to strike a balance between this logic and RC component of this overall self-time path. So classical self-time tactic might not actually work if we really want to push for that speed. Okay, so I'm just showing this block diagram. It is actually explained in a lot more detail in the paper, so I will really request you all to go through it once. So I'm just showing this picture. It is actually the vertical part of the design. So we have some local controls, and we have some of the decoding parts where actually the word line would be generated. So this would actually scale with the increase in height. So it would actually keep on increasing this part with the number of rows increase in memory. Okay, so then there's there's this sense amplifier logic, which is actually kept here, and then again this part. So in this case, I'm actually looking at the two-port memory, so that's why you see two different kind of signals, read and write. Okay, so what essentially we are trying to do in this case, we are not using complete logic that we were trying to see. If that would happen, then it's all good. But again, there's some RC component which has to be there, so that you could actually keep the design robustness also intact. Okay, so that's why we create these two kind of signals. So when we are talking about the bit line tracking, then we are bringing in these two kind of signals. So they would actually track this vertical RC. So what essentially we are trying to do, instead of creating those delays which you can actually do with logic stages, just do it with RCs, so that when the height is increasing, you could control it, and it could actually track itself, and then it could bring in that RC component that you need in the overall self-timing path. Okay, and so these are those signals which actually create a kind of faster path for you in case of on high speed. So and we also use this kind of mux where we still keep this earlier classical bit line tracking intact, because when you are working at really low voltage, then the variation control is actually a lot more complicated. So there you want to actually track them in the best possible way. Okay, so that is still intact, and we introduce this bypass kind of path which you can use when you are scaling for that high speed. Okay, so let me move on to some simulation results. So first, these charts are actually showing some access time and the write pulse, read pulse numbers at really high voltage. So if you look at these charts, you will notice that the small instance has not scaled as good as we want, because that were actually mostly dominated by logic. So when we are increasing the voltage, it was still going good. So that's why we're using this method, we are not seeing the improvement. But if you look at the big instances, they are actually improving by up to 40, 30, 45%. Okay, and the reason is actually pretty simple, that because earlier in the earlier method they were actually dominated by RCs, which we have actually tried to replace with a combination of logic and some tracked RC element. Okay, so that's why we see the most improvement there. In these charts, what I'm trying to show, when we actually created a faster mode, which was a combination of logic and RC, which was dominated by actually logic. So what could happen? Let's say we are working at a lower voltage. Then at lower voltage, these logic stages that we had brought in fast mode, they might start showing much more delay. Okay, so it is very important when we are working at low voltage, this faster mode still remain faster. Otherwise, it could be a problem when we are trying to scale this, in the post silicon results. Let's say the silicon got better and you want to actually improve from the mode you did the actual timing sign off, and you want to scale speed, and if it is not fast enough, then you cannot actually do it. Okay, so in this case also at lower voltage, you want to make sure that the faster mode still remains faster. So that's what we try to check once we implement that faster mode, that even at lower voltages we are actually seeing good improvement, some improvement, because it still has to be a faster mode. Otherwise, you might actually start slowing down while actually going to a faster mode when you are working at low voltage. Okay, so I would conclude by saying that this proposed method actually defines a very good way to create that fastest timing mode possible from the design, and that too definitely without compromising on the design robustness. So you have to have a fastest mode possible from your design, which can be achieved when you have the positive, when the silicon is on the positive side, and also when you want to actually scale speeds. Okay, and as I said, as well, I was mentioning that it is also very, very useful when you are going for post silicon speed boost. When you saw that okay, the silicon is performing better, then I want to probably push for a faster mode. I mean, moving on from the mode which I did the same time sign off with. Okay, so this is all from me. Okay, thank you. Thanks so much, and I would be open to any questions.
Good morning, everyone. I am Feraz
Thank
Hussain.
you very much.
It's my honor to present my research work in the 34th
Yeah, maybe we
International
need to
Conference
stop
on
now.
VLSI Design. My topic of presentation is a 0.4
Please
microamp
stop the video.
offset, 6 nanosecond
Stop the
sensing
video.
time, multi-level sense amplifier for resistive non-volatile memories in 65 nanometer LSTP technology. Authored by Feraz Hussain, Bilal Iqbal, and Dr. Anuj Grover. Since every research is built on motivation, we are not apart from it. Physical
Stop the
limitations
video.
in scaling of non-volatile memories necessitates alternative ways to increase on-chip storage density. And new generation NVMs offer advantages in terms of speed and can enable replacement of embedded volatile RAMs. Further, storing multiple bits in a single cell enables reduction in cost per bit. Therefore, we studied various essential sense amplifier design techniques such as offset voltage cancellation, double sensing margin, strong positive feedback, etc. to achieve a parallel sensing multi-level sense amplifier for resistive non-volatile memories with faster and stable read operations. First, I will cover basics of the offset cancelling current-based sense amplifier, then design of the enhanced OCCP SA. Thereafter, multi-level sense amplifier design for resistive non-volatile memories, followed by comparison and conclusion. Offset cancelling current-based sense amplifier involves two-phase sensing operation. One is pre-charge phase, P1, and second is amplification phase, P2. At the beginning of pre-charge phase, switches S1, S2, S3, and S4 are turned on, while two switches DS1 and DS2 are off. The diode connected transistor M1 and M2 provides pre-charge current I pre1 and I pre2 to the bit line and dummy bit line, along with ICEL and IREF. Despite the process variation in M1 and M2, current IM1 and IM2 becomes ICEL and IREF after enough pre-charge time. At the end of P1, voltage V cell
Hello, by mistake, this video got played by everything by the team. Hello, Parth.
Yeah. So I think
we can
we went
actually
quite a bit on that other presentation.
Yeah.
So maybe what I propose, I don't know, I think there are 2-3 slides which went past. So do we need to club it
It's
later?
fine. So we can have actually question answer session for Krishnanand Mishra paper, and then we can proceed for
Exactly.
third.
Yeah. Okay. So any questions?
From web, we don't have any questions, but what I can ask 1 or 2 questions to Krishnanand Mishra maybe. So in general, whenever you are saying high speed and this processor speed are going up to 4 gigahertz, what is the current state of art memory speed, whatever you have designed? So in terms of gigahertz and all those.
Yeah, it is in the. I mean, this work actually was done on 7 nanometer and close to that, of 7 and also in 5. So on 7 nanometer, we could actually design these kind of high speed memories close to 3.3 and 4 gigahertz only. So there would be some set of memories which we really want to use at as part of L1 and L2. So they were in those range, but they were only selective memories, and that's where we want to hit for these speeds.
Okay, so in general, what happens whenever you are going processor up to 3 gigahertz or 4 gigahertz, power consumption is an issue. But in case of whenever for memory also, so it will be again problematic case. So in general, whenever you so we want not to use the speed. So suppose you are taking a bike, so it's actually 120 maximum speed is 120, but in general we go at actually 50 or 60 speed.
Right. So that's why. Right. I agree with you, and that's why we always have this combination of memory elements that we want to use. We won't be using actually too many of such memory instances which are not really high speed. They would mostly lying in the L1 and where we really want to hit speeds. But the rest of the memories, they are still the high density kind of memories which are running fairly slow. Which could meet the requirement of the applications. So there would be a mix of it, but there would be places where we need out and out the speed. So then these kind of memories would come into picture and they can play that role.
Okay, let other people ask questions. Parth?
Yeah, I'm good. Darren.
Do you have any questions you can ask?
I have no questions at the moment. Yeah.
Otherwise, we can proceed for the next step.
Yeah. Thank you, Krishnan.
Thanks, Partha.
Yeah. Thanks. So let's move to the next one, which we have already seen a glimpse of it.
So we have already two authors.
Yes.
We have two authors,
exactly.
Bilal and Feraz. So another author for the next paper, they will be able to answer our queries.
Exactly. Yeah. So let's continue. It's a 0.4 microampere offset 6 nanosecond sensing time multi-level sense amplifier for resistive non-volatile memories in 65 nanometer LSTP technology. Faraj, he had started his presentation. Let's hear it. Let's continue to hear this.
Good morning, everyone. I am Feraz Hussain. It is my honor to present my research work in the 34th International Conference on VLSI Design. My topic of presentation is a 0.4 microampere offset 6 nanosecond sensing time multi-level sense amplifier for resistive non-volatile memories in 65 nanometer LSTP technology, authored by Feraz Hussain, Bilal Iqbal, and Dr. Anuj Grover. Since every research is built on motivation, we are not apart from it. Physical limitations in scaling of non-volatile memories necessitate alternative ways to increase on-chip storage density. And new generation NVMs offer advantages in terms of speed and can enable replacement of embedded volatile RAMs. Further, storing multiple bits in a single cell enables reduction in cost per bit. Therefore, we studied various essential sense amplifier design techniques such as offset voltage cancellation, double sensing margin, strong positive feedback, etc., to achieve a parallel sensing multi-level sense amplifier for resistive non-volatile memories with faster and stable read operations. First, I will cover basics of the offset cancelling current-based sense amplifier, then design of the enhanced OCCP SA. Thereafter, multi-level sense amplifier design for resistive non-volatile memories, followed by comparison and conclusion. Offset cancelling current-based sense amplifier involves two-phase sensing operation. One is pre-charge phase P1 and second is amplification phase P2. At the beginning of pre-charge phase, switches S1, S2, S3 and S4 are turned on, while two switches DS1 and DS2 are off. The diode connected transistor M1 and M2 provides pre-charge current I pre1 and I pre2 to the bit line and dummy bit line, along with ICEL and IREF. Despite the process variation in M1 and M2, current IM1 and IM2 becomes ICEL and IREF after enough pre-charge time. At the end of P1, cell voltage VCell and reference voltage VCell are stored in capacitance C1 and C2 respectively. In the amplification phase, the four switches S1 to S4 are turned off, while two double sensing margin switches DS1 and DS2 are turned on. The introduction of these two switches serves as data-dependent reference generator and generates strong positive feedback. The transistor M1 charges this node VCell with the current IM. At the same time, the switch DS1 will discharge this node VCell with the current IREF. Therefore, the total current difference between node VCell and node VREF will be twice of delta I, where delta I is difference between ICEL and IREF. Simulated waveform for the case when ICEL is less than IREF is shown in the figure. When ICEL is less than IREF, it leads to an increase in VREF that causes lowering of IM1 due to AC coupling behavior of C2. Eventually, this IM1 lowering leads to a monotonic decrease in VCell, which is shown in this figure. Hence, a combination of double sensing margin and strong positive feedback in OCCP SA result in a faster sensing time. The offset cancelling current sense amplifier holds the high read stability characteristic even in the presence of device mismatches M1 and M2. Here we are explaining this high read stability using case when the reference current is greater than the cell current. In pre-charge phase, current IM1 should be smaller than IM2 in the absence of device mismatch as shown in figure number 3b. Here IM1 is smaller than IM2. However, in advanced technology node, there will be process variations which may lead to a larger IM1 and hence incorrect current sampling in pre-charge phase as we can see in figure number 3b. Now at the beginning of amplification phase, VCell starts to decrease because of the discharging current IREF flowing through the switch DS1, and finally effect of the strong positive feedback decreases cell voltage VCell till ground. So the wrong current sampling during pre-charge phase due to the device mismatches will be corrected by the OCCP SA. While state-of-the-art OCCP SA we examined so far offers very prominent merits, but it suffers from the power overhead caused by a clamp voltage, which gets aggravated in multi-level sense amplifier design. So we propose a new current sense amplifier structure which is known as enhanced offset cancelling current based sense amplifier, and down the line we will be using the word EOCCP SA, which is combined with a voltage latch sense amplifier that is shown in figure number 4. We can see signals pre and M have been introduced to control the switches S1 to S4 and DS1 DS2. The voltage latch SA will be enabled by signal SAEN and used to generate the digital signal either 0 or 1 based on the EOCCB SA output VCell and VREF. The consolidated sensing time Tsyn of the proposed EOCCB SA is given here, where T-pre and T-amp is the precharge time and amplification time of the EOCCB SA, while TSAN is the time during which SAN signal is enabled. For clarity, a complete sequence of the signal associated with the circuit is shown in the figure number 5. The design has been implemented at 1 volt in 65 nanometer LSTP technology, and 4000 Monte Carlo runs have been done across the entire range of PVT conditions to characterize the EOCCB SA. We ensured the design robustness until 0.85 voltage while keeping the sensing time of 6 nanoseconds. In pre-layout simulation result, we noticed that the EOCCB SA has very low 3 sigma offset for a very wide range of current, that is from 20 microampere to 70 microampere. This is significantly better than other state-of-the-art current sense amplifiers. The EOCCB achieves a minimum of 3 sigma offset of 0.4 microampere for reference current 27 microampere, whereas sensing time is 6 nanosecond. We designed the layout in a common centroid topology and recharacterized our design. The comparison of pre-layout and post-layout result is shown in this figure number 7. It is evident that the low offset range as seen in the pre-layout result has been maintained in the post-layout analysis, and it achieves same yield as offset cancelling current sense amplifier without a clamped voltage. That is why it consumes much lesser power, which is 59.38 microwatt, while supply voltage is increased to 1.1 volt in fast corner for 125 degrees centigrade. In multi-level sense amplifier design, maintaining the faster sensing time and high storage density at desirably small power is of prime importance. Therefore, we can safely assume that the proposed EOCCB SA can be used for multi-level sensing in advanced non-volatile memories. Here we come to multi-level sense amplifier architecture. For parallel bit sensing, we propose a sense amplifier based on a parallel sensing scheme using EOCCB SA. In the design, a cell current concurrently compared against 3 reference current IREF-A, IREF-B, IREF-C, and the 3 output QA, QB, QC are generated. Now these 3 outputs QA, QB, QC are used to determine 2-bit data MSB and LSB using this algorithm number 1, which is shown in figure number 9. Layout implementation of the proposed multi-level sense amplifier in 65 nanometer LSTP technology is shown in this figure. The width of the I/O has been limited to 66 micrometer for a MUX2 layout configuration, and total area required for our implementation is 151.2 micrometer square. In the design, we have used 3 reference current, 21 microampere, 33 microampere and 48 microampere, which lie in the low offset region of the EOCCB SA as we showed it in figure number 6. To characterize the multi-level sense amplifier design, ICL is varied from 19 microampere to 50 microampere. As offset value of the EOCCB SA changes with reference current IREF, the multi-level sense amplifier will have 3 offset value, which is summarized in table number 1. In the Monte Carlo simulated waveform, we show that the designed multi-level sense amplifier is stable even in the presence of timing mismatch between pre-charge phase and amplification phase. So the resilience of the EOCCB assay is maintained even in the parallel multi-level sensing architecture. Finally, a post-layout power estimation on the fast first corner at 125 degrees centigrade is performed, and total average power at 1.1 volt VDD is evaluated to 232.7 microwatt. Here we benchmark PPA of the proposed multi-level sense amplifier with previously compensated multi-level designs, where NA means not available. Concluding this work, we first enhanced the OCCB assay design. Then we proposed EOCCB assay, which is 40% faster and denser than state-of-the-art OCCB assay. We then included the EOCCB assay into a 4-level sense amplifier based on a parallel sensing architecture. The proposed multi-level design has 25% sensing speed than previously realized parallel sensing designs, while consuming 28% lesser average power. It is also 20% denser than serial sensing scheme in the same 65 nanometer technology. So the proposed design is better in all three PPA axes of power, performance and area. Here we have mentioned some of the references. And finally, thanks to all of you. You all have been a great audience.
Good morning, everyone.
Thank you, Faraj. So again, I leave it open for questions. Arimata, do you have some questions?
So I think we have 2 questions, but not for this particular paper. It is for earlier paper. Let me ask for this paper. Let me ask one question. Why is 65 nanometer? Why is it not lower than the lower technology node?
Good morning, sir. Am I audible?
Yeah, audible.
Yeah, actually, we had the liberty to use only 65 nanometer. Now we have in our institute 28 nanometer so far, but at that time when the research was started, then it was only 65 nanometer LSTP.
Okay, I have this question, and from the audience also were not getting any questions, but all the questions are from our previous paper. So, okay, I don't have any questions, sir. Session chair can Partha can have.
So yeah, so maybe you explained this during the paper, but maybe if you can take us through how you're getting the density improvement when you have this new circuitry.
Sorry.
You mentioned that you have about 20% denser circuit right now.
Yeah.
Could you elaborate that a bit?
Yeah, actually, the circuit technique, I mean, designing was actually the mind. When I started doing designing, then it was my first. I referred the OCCB assay, which had extremely good characteristic in terms of double sensing margin and the offset parameter. But there it was a certain that I first I realized on that myself, and then I found there was some transistors that can be neglected. I mean, I can remove from my circuit and without any performance loss. So in that case, what I did, I optimized the circuit to the certain extent level, since that should my circuit should be as minimum as possible in EOCCBSA case, and that was the smallest circuit building block that I got from there. And after that, when I integrated, there was no extra transistor at all. So when I finally integrated out the circuit, and I mean, I benchmarked with previously designed multi-level sense amplifier. Then I got it the what area they proposed in the same 65 nanometer technology. Mine was 20% lesser. I mean, it completely was the design technique, nothing else.
Okay. Thanks for that. So any more questions?
There are two questions for earlier paper. So Krishnanand Mishra is still available. Why not to
Yeah,
ask
we
that two
can.
questions?
Yeah, we can maybe. Yeah.
Before going to the next paper, let's ask that two questions. So
Yeah, sure,
Praveen
sure. Yeah.
Verma, he asked that questions
Mhm.
to Krishnanand Mishra. I think so. How the solution is differentiating compared to use the track cells?
Yes. So actually, as I was explaining during the presentation, also that we have one already in a classical method where we do the complete tracking. But the problem arises when we are actually going to a higher voltage, and we are not able to scale speed. So the limitation is only because of the RC elements which we are using as part of the self-timing circuitry. But those are also important. Okay, so we cannot get rid of all of them, otherwise it would be too difficult to control this complete path. So ideally we always want that complete tracking to be there, but when we want to scale those high speeds, we want to at least replace a part of it with logic, because otherwise we won't be able to scale them. So that was the basic reason why we had to move away from classical speeds, because we might not need those kind of bigger loops at such high voltage when the bit cell overall uh, performance is also going better. So that was the reason how it actually turned out to be different, that RC elements are still there, but only to create delay, but not to do the complete tracking that we use in our classical methods.
Okay. So another question is why we should not use the track cell design for this? Some question, I think so.
So it's the same reason, right? I mean, we always want that those the classical methods to be there, where we do complete tracking, and and that's the way the designs are best in terms of design robustness and reliability. But when we come to high speeds, there the variation also is going down, and also these signals are not supposed to be completely full scale. What I mean, when we are working at really high voltage, let's say in this case 855, so it might not reach to that 70-80% limit. Even much before that, bit cell can start writing. Okay, so that actually gives us a hint that we might not need complete tracking. We can do something and probably strike a balance to keep something part of it to logic, which would start giving us scaling in terms of speed. So that's how it becomes different from the fully tracked design.
Okay. Thank you, Krishnanand Mishra. We can go for the next paper.
Yeah.
Thank you.
So
Thank you.
Thank you very much. So the last paper of the session, this is a low latency stochastic square root circuit. It's the work from Jadavpur University, and it will be presented by Shyam Mitra.
Good afternoon to dear madams and sirs and my fellow friends. Myself, Shambhala Mitra, Assistant Professor in the Department of Instrumentation and Electronics Engineering from Jadavpur University. I am here to present my paper titled A Low Latency Stochastic Square Root Circuit. I am thankful to my fellow mates, my fellow co-authors, Debojyoti Banerjee and Professor Meena K. Nashkar, to bring this paper in this present form. Now, the stochastic computing has shown promise over the years due to its relative simplicity in hardware design, enabling low power compared to the conventional computing paradigm. The error tolerance and the hardware efficient solutions of SC have made it extremely popular in a variety of applications, starting from low discrepancy sequences to image processing tasks. In SC, a number is being represented in a string of ones and zeros, where the numerical value is given by the total number of ones occurring in the bit string divided by the length of the stochastic bit string. For example, a number within the range, which is obviously 6 by 8, can be represented using the bit string 11011111. There can be several other representations of it. That means there is a shuffling of the positions of 1 and 0 which can be permitted. Thus, SC, unlike the binary weighted encoding scheme where each binary bit is associated with a weight and most significant bit carries the highest weight. Therefore, any change in the MSB position will greatly affect the overall decimal value. But in contrary to that, in stochastic computing, the numbers are represented in probabilities, and there are no such weights assigned to the bits such that if any one of the bit gets flipped, then the total number of then the total change is depicted in the average value, that is the number of bits being flipped. One of the most useful application of the stochastic computing is obviously the multiplication, which can be done using a simple AND gate. For example, a number with probability px is equal to 6 by 8 represented using the bit stream 1101011011, and a number with a probability value p4 by 8 can be represented using the stochastic bit stream 100111001. Then the output bit stream can be obtained by just ANDing the two bit streams, which is nothing but 100111001, which is equivalent to Pz is equal to 4 by 8. Now, coming on to the square root, which is the material to concern in this manuscript. It is widely used as one of the important arithmetic operators in several operations like calculations of standard deviations, solutions to nonlinear equations, and used in several image processing algorithms. Now, there are few notable implementations of SSRC, and the first one accounts to the circuit that has been realized by Gaines in 1969 using an ADDIE block. It is nothing but a counter with negative feedback to minimize the error between the square of the obtained square root value and the actual value of the number. One of the major disadvantages that this circuit faced was the slow convergence requiring multiple iterations to get to the square root value, which restricted its use in real-time applications. To overcome these disadvantages, Torah et al. Proposed a circuit in which multiple random number generators were used to eliminate the correlation between essences. Thus, the squaring operation could be accurately performed, but at the cost of increased hardware complexity. More recently, a stochastic square root circuit has been proposed by Wu et al. That reduced hardware by eliminating this saturated counter as in the previous cases, but that too produced inaccurate results in lower range of inputs from 0 to 0.2. Thus, these shortcomings led us to think of the SSRC, which could accommodate these errors and may actually reduce these errors to a certain extent. The proposed square roots unit consists of two basic blocks. One is the division block and another is the addition block. The inputs to this block are nothing but the Pin, whose square root is to be computed, and the initial guess value PGS, and the output to this block is the square root value, which is PSQRT. So first one is the division block, which is implemented using the Kordif block. One of the input to the Kordif block comes from the input S and Pin, and another from the last iteration PGS. For a Kordif block to perform accurate division, the inputs must be positively correlated. Next comes the adder block, and we have implemented this adder block using a 2:1 mux, which can work on both the correlated as well as uncorrelated input bit streams. The output of the Kordif kernel, PDIV, and the input of the Pin are the two inputs of the multiplexer. The select input of the multiplexer is an XOR combination of the previous select and the two inputs PDIV and PGS. We have proposed an iteration control unit whereby we can limit the number of iterations involved in the computation of SSRCs. This can help us to achieve an ideal trade-off between the accuracy and the number of iterations required to compute square root value. In several image processing tasks like binarization, contrast stretching, etc., involves computation of the square root. In such applications, it is possible to reduce the latency involved by incorporating approximated result, thereby lowering the accuracy without severe degradation in the image quality. Now, the first block that we encounter in this iteration control unit is nothing but a squarer, which performs stochastic multiplication of the same number. You can see here that we have introduced a shuffle buffer, which reduces basically the correlation between the two numbers that is a requisite to the AND gate. The shuffle buffer consists of a multiplexer, it 3D flip-flops, and a random number generator generating numbers between 0 to 1, so to produce reduced SCCs between the inputs, leading to accurate squaring operation. Next comes in, before the subtractor block, there is a synchronizer placed. The function of the synchronizer is to exactly pair up the number of ones and zeros maximally, so that at the input of the subtractor unit, two of the bit streams are positively correlated. This is required as because in the subtractor block, we have used an XOR gate, and it is the property of the XOR gate that in the XOR gate performs exact subtraction when the two numbers are positively correlated. So synchronizer does that for subtractor unit. Next comes in the comparator block, which is the most essential part of this design. The comparator circuit compares the obtained square root value with the desired level of accuracy. It is based on the fact that when two correlated inputs are given to an AND gate with an inverter to one of its input, the stochastic function implemented is given by the maximum of the two numbers. This property is utilized in this case, and when PDIF-S, which is the output from the synchronizer, is lesser than the error tolerance of the proposed application P-RES-S, which is the output from the synchronizer, which is also an output. So a bit stream of zeros is obtained at the comparator's output, which indicates that the square root value is predicted satisfactorily. We have produced here two different approaches and compared them with respect to latencies. So the first representation is the representation of the square root circuit using the fixed length stochastic bit stream. In this scheme, the length of the stochastic bit stream is kept constant throughout all the iterations. As assuming that the serial mode of operation is valid and that a single square root block is used to process 256-bit SN, a control signal is generated after each 256 clock pulses that updates the obtained square root value to PGS. In low responsive applications that suffices with a given level of accuracy and latency, we can use this arrangement as shown here. It is observed that for 256 fixed length bit stream, the error reduces to less than 0.02 in two iterations, that is in 512 clock pulses, and similarly for 128 and 64-bit fixed length bit stream, the error reduces to less than 0.1 and 0.2 respectively, requiring 512 clock pulses. Our next proposition is with the variable length stochastic bit stream. In this scheme, the length of the SN is not fixed and is gradually increased in each iteration. This kind of applications are required when it is desirable to have a low latency in order to implement real-time applications. So, in this case, a very possible way to decrease the latency of SSRC is to decrease the length of the stochastic streams. So, in the proposed SSRC, the length of the stochastic bit stream is varied in an incremental way to arrive at the desired accuracy. Initially, the square root using 64-bit SN is computed using the SSRC. Then the lengths of the stochastic bit streams are increased in the order of 2 to the power n, such that the subsequent iterations consider 128, 256, 512, and so on until the desired accuracy is met. It is observed that the square root computation requires 448 clock pulses to complete the third iteration and to reach an average error less than 0.02. Thus, here you can see that a significant number of clock cycles can be saved in introducing the variable length bit stream in each iteration. The complete block diagram of it shows it all. Here is the summary of the hardware comparison when the proposed technique has been compared with the two state-of-the-art methods. It is seen that the proposed technique consumes much lesser area compared to Toral et al. As because the circuit of Toral et al. Uses multiple SNGs to generate the stochastic numbers, where the proposed circuit uses only one SNG. So it is a significant advantage compared to the other state-of-the-art techniques. Here is the result of accuracy after 2 iterations. We have calculated the accuracies in terms of the average error, which is obtained after 2 iterations. We have considered 4 fixed length bit streams. First one is the 256 bit fixed length bit stream. B is with the 128 bit fixed length bit stream. C with the 64 bit fixed length bit stream, and D is with the 32 bit fixed length bit stream. We have seen that using the 256 bit fixed length bit stream, the average error is the least, whereas for 32 bit fixed length bit stream, the average error is the highest. Here are the iterations that we have achieved after using the specified tolerance limit using this variable length bit stream scheme. In the x-axis, we have plotted the input range, and in the y-axis, the number of clock pulses to achieve the required accuracy. Here we have done stochastic implementation of an image enhancement technique, which is basically a contrast trait on images. We have studied on random images taken from a standard dataset. And we have observed that the structure similarity index SSIM for the proposed method is the highest and is very close to 1 compared to the other 2 methods, which shows a significant advantage of this method compared to the other state-of-the-art methods. So, in this proposed work, an SSRC has been demonstrated, but the accuracy can be defined according to user's choice. A method is also suggested whereby the length of the bit stream can be compromised based on the accuracy, so that reduced latency operations can be achieved at the end. Also, a comprehensive study between the proposed method and the existing state-of-the-art methods has been discussed, which established the reliability of the circuit in the context of lower range of inputs requiring less hardware. The proposed circuit can accurately implement contrast trait in images with higher SSIM index, which is indicative of the fact that it can be applied to other image processing tasks also. In future, the proposed SSRC can be used to accurately design real-time image processing applications with lesser hardware complexity. Also, other iterative algorithms can be tried out to obtain their stochastic implementations using lesser hardware. Thank you.
Hi everyone.
Thank you very much, Shamli Mitra. The session is open for questions for this paper. Arivarta, do we have some questions?
Yeah, for this session also, for this paper also, we don't have any questions from the audience. I think so maybe technical part, maybe we're not able to get questions maybe, but we can ask 1 or 2 questions. So let me ask very simplistic questions. So the square root unit, so what the targeted applications you're saying, image contrast enhancement. Any other applications have you targeted or only this? Hello? Shamli Mitra. So we're not able to hear you.
No, yeah, I think there's a problem with the microphone for Shamli Mitra.
Yeah.
Okay, so we just hold on for a few seconds. If she's able to comment, it's okay. Otherwise, we can take it offline and.
We can take it offline. Otherwise,
yeah, definitely. Thank you very much. I think it's a.
Thank you very much, Ashok. So thank you, Parthasarathy, for sharing the session. So we are giving you a virtual token of appreciation for sharing the session. Okay. So and we'll ship the physical token of appreciation to your mailing address. Okay. Yeah. And thank you all the presenters. Thank you all the audience of the sessions. Thank you all the team member of the technical sessions. now we can say, now we can close this session, Parthasarathy?
Yeah, yes, we will close this session now. I think
now technically session 1 is formally concluded, and we'll meet after the lunch at 1:30 p.m. For the keynote of the conference. Now we're formally closing. Yeah.
Thank you. Bye.
Thank you.
Hello.